Okay, for the Module 3 Mastery Assignment for AP Calculus BC, this module is focused on series, sequences, a Maclaurin series, Taylor series, and a number of different tests to test for convergence and divergence. However, we're only going to focus on two topics today, but they're both very important and will most definitely show up on the AP Calculus BC exam. And the first topic I'm going to cover are going to be comparison tests, and the second are Taylor series. So let's begin. Let's get started. Okay, so the first topic we're going to cover are comparison tests. And you use comparison tests to determine whether a series is going to be convergent or divergent. There are a number of tests actually that you can use for convergence and divergence. Here are all of them. However, today we're just going to focus on direct comparison test and limit comparison test because all these different tests, there's so many, we're just going to focus on these two. So for the direct comparison test, if you're given a series a sub n and a series b sub n, where a sub n is less than or equal to b of n, but is greater than 0, these two rules apply. If a sub n diverges, then so does b sub n. If b sub n converges, then so does a sub n. Here are some important reminders for the direct comparison test. You need to show your inequality in any work for the AP exam. To prove convergence, the terms of the series must be less than the terms of a known convergent series, and to prove divergence, the terms of the series must be greater than the terms of a known divergent series. Okay, so let's go into some examples. So if we're given the series 1 over n squared plus 1, we know this is very similar to 1 over n squared because this is a p-series test, which is easy, and we know that since 2 is greater than 1, that's going to converge. And here, when we use our sign of equality, the example 1 over n squared plus 1 is less than 1 over n squared, so that's going to converge. So the next example, 4 over 5 plus n raised to the n. We know it's very similar to 4 over 5n, which is actually going to be a geometric series. And we know that 4 over 5 raised to the n converges, and when we compare this to the other equality, we know that it's convergent. Okay, so the next test we're going to talk about is the limit comparison test, and we're going to basically be finding the limit of the ratio of the two series. If that limit is greater than 0 but not infinity, then the two series do the same thing and either both converge or diverge. If you get an answer that's infinity, this is okay provided that the known series is divergent. This is the same case if we get an answer that's 0, provided the known series is convergent. So given a series of a sub n and a series of b sub n, where a sub n is greater than 0 and b sub n is greater than 0, we can calculate the limit as n approaches infinity of a sub n over b sub n. And this limit, if L is greater than 0, both either converge or both diverge. If the known series converges and L equals 0, both converge. If the known series diverges and L equals infinity, both diverge. So let's look at a couple examples. Okay, so the first example we're going to look at is the series as n equals 1 goes to infinity, n squared over n to the 5th minus 4. That's going to be our a sub n, and our b sub n is going to be the series from n equals 1 to infinity of 1 over n to the 3rd. We know 1 over n to the 3rd is convergent because of our p series. P is greater than 1 here, which is our p equals 3, so it's going to be convergent. But we're going to take the limit, like our rule says, the limit is n approaches infinity of a sub n over b sub n. So basically, you take n squared over n to the 5th minus 4, divide by n to the 3rd, which is just going to be multiplied by the reciprocal. And then you're going to get the limit as n approaches infinity of n to the 5th over n to the 5th minus 4. And then n to the 5th over n to the 5th, because this is we can kind of look at it like our limits. They're the same degree polynomial, so you're just going to get 1. And we know that they both converge because that our L is greater than 0 and b sub n converges. Okay, so the second problem we're going to look at is this series as n equals 1 goes to infinity of 2n over n squared plus 2. So that's going to be our a sub n, and our b sub n is going to be the series n equals 1 to infinity of 1 over n. And that is divergent, that's the harmonic series, we know that. And so we're just going to set it up as the rule states. We're going to do a sub n over b sub n. We're going to take the limit as n approaches infinity of 2n over n squared plus 2. We're going to multiply by the reciprocal because we're dividing by fraction. And then you get this is equal to 2 when you take this limit, because you have just basic limit rules, 2n squared over n squared, because they're the same degree polynomial, so you get 2. And because that we get this number, and the first series, the b sub n, is divergent. We know the two series are going to do the same thing because the limit is greater than 0, but it's not infinity. Okay, so the second topic that we're going to look at are Taylor series. And we've actually had some kind of experience with Taylor series before in Calc AB, actually, but we probably haven't realized it. But we've learned how to construct a first-degree Taylor polynomial, actually. A first-degree Taylor polynomial approximation of any function is actually when you find the equation of a line tangent to a function at a particular point. You're finding the first-degree Taylor polynomial. But anyway, this is the, here's an important and interesting fun fact. But the equation that was just on the whiteboard or the paper is going to be your basic equation to set up a Taylor polynomial. And that's just going to be f of n, so the nth derivative of c being your center, x minus c raised to the n over n factorial. And then you're going to get f of c plus f prime c, x minus c, f second derivative, c x minus c squared over 2 factorial. And that's basically how that's going to work. So let's jump into some examples. Okay, so our first example is, let's let f be a function with f of 3 equals 2, f prime of 3 equals negative 1, f double prime of 3 equals 6, and f triple prime, or f to the third degree of 3 equals 12. Which of the following is, or construct a third degree Taylor polynomial of f of 3 about 3. So about 3, we know 3 is going to be our center. Let's write down all of our given information. F of 3 equals 2, f double prime of 3 equals 6, f prime of 3 equals negative 1, and everything is given to us. And we know Taylor polynomials are constructed in the same way. F sub n of c of n prime over n prime times x minus 3 raised to the n. And so basically, since they've given us all of our important information. We don't have a series per se, but we know we have our center is 3, and because it's asking us for a third degree, and they've given us the 3 derivatives we need, we have the function, original function, f prime, f double prime, and triple prime. So we can construct our Taylor polynomial by just plugging in that 3 for the center into our equation, and plugging in 0 for n, 1 for n, 2 for n, 3 for n. To get our third degree Taylor polynomial, which is 2 minus x minus 3 plus 3 times x minus 3 squared plus 2 times x minus 3 raised to the third power. Okay, so the second example we're going to look at is determine the Taylor series representation of e to the negative x squared. So the approach we're going to take about this for this one is we're going to look at what we're given, and we're going to look at what we know, and with some modification, we will be able to come up with an answer. So we know one of our known series that we know is e to the x of the series is equal to, or the function e to the x is equal to the series of x to the n, x raised to the n over the factorial of n, which is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial. So what we're going to do is we are going to treat this negative x squared as the x in the series that we know for e to the x. And so basically what we're going to do is we're just going to sub this negative x squared in for every x value that we see. And when we do that, we come up with 1 plus negative x squared plus negative x squared over 2 factorial plus negative x squared raised to the third power over 3 factorial, etc., etc. And so this is just going to be equal to 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus ... etc. It will go on and on and on. And that's how you would determine the Taylor series representation of e to the negative x squared.